In this lesson, we're going to apply properties of rational exponents. So here are your properties again, with dealing with exponents in general. And they're all the same. The only difference is if you look in the examples, you'll see that we're using rationals instead, fractional exponents. But everything here is still the same as far as how these work. The exponential rules. So let's put these to use and see how they would work for these particular problems. So in my first example, I have I have 5 to the 1/3 times 7 to the 1/4, and that's all to the third power. So the first thing I want to do, well, there's more than one approach here, but notice that these have different exponents, and then I have a 3 on the outside here. Well, I'm going to go ahead and multiply, use the power of a power property here. So this is going to give me 5, and then 3 times 1/3 is just 1. Okay, 5 to the first power, or just 5. And then I'm going to multiply 3 with 1/4, so that's easy to do. That's going to give me, so times 7, and then to the 3/4 power, like so. And really that's all I can do. These are not like terms, but I would not include the first power here. That's assumed. So, I would box that answer in. On B, here I have 10 over 10 to the 2/5 power. And with this, so remember we have a quotient of a power, and I'm going to be subtracting the exponents. Now the exponent on the numerator here is going to be 10 to the first. But since I'm going to be subtracting 2/5 from whatever's up here, the 1, I'm going to rewrite this as a fraction as 5 over 5. So therefore, I'm going to have 10 to the 5/5 minus 2/5, which is simply going to be 10 to the 3/5. One thing I want to point out here is we can only do this because the bases here are the same. Okay, they're both 10. If they were different, we would not be able to do this. So please note that the bases are the same, and we can only do it if the bases are the same. So there we have it, 10 to the 3/5, and I would box that one in. Okay, so with this one, I would go ahead and take care of the negative 1/6. It's just like that first one, except we have a negative here. And well, again, there are different ways we could approach this. I could evaluate the negative first, and then deal with the 1/6, or I can just multiply it all as a negative 1/6. It doesn't matter. I'll just go ahead and, since this whole thing is to the negative 1/6, I'm just going to go ahead and drop it into the denominator. So that's going to be 2 to the 6th times 4 to the 6th, and then all that to the 1/6 power. And then from here, I can use the power of a power, and that's just going to be give me 2, so equals 2, because 6 times 1/6 is just 1, and then times 4, and then I evaluate that. That's just going to be 1/8, and then I would box that one in like so. So in this one, I have 56 to the 1/4 power over 7 to the 1/4, all to the 5th. Now when I evaluate this, I notice that both of these are to the 1/4 power, and I could use the quotient of a power property in reverse. Would be one method of doing this, and I could just rewrite this as 56 over 7 and then all that to the 1/4 power, and then I would take all that and put it to the 5th power. So then all I have to do is divide 7 into 56, and then that would give me 8 to the 1/4 to the 5th, and then I would just multiply, or use the power of a power and multiply the exponents, so 8 to the 5/4 power. That would probably be the most efficient way of doing that one. So, and it just takes practice. The more you do these, the more you see these sort of things and know what maybe the easiest way of doing it is. You may not always do it the easiest way the first time through, but as long as you get there, you'll be fine. Okay, so let's look at some of the properties of radicals. One of the product property of radicals simply is that if we have the nth root of a times b, it can be separated out as the nth root of a times the nth root of b, and the quotient property of radicals is the same thing but with division. So we could separate out the numerator and divide denominator with separate radicals, and provided that b is not equal to 0. So we'll look at some examples of that. For instance, here I have a is the cube root of 125 times the cube root of 8. So when I evaluate something like this, I can just work these out individually and then multiply them together, or I could just multiply these together and then find the cube root. So I could do 125 times 8, since since these are the same, okay, and that's going to give me 1,000. So I'd have the cube root of 1,000, and so then the cube root of 1,000 is just 10. Okay, sometimes you get things that are not perfect cubes, and it's good to multiply together. So I'm just illustrating the property and how that would work. So know that you can do that. Likewise with b here, I think b might show it a little bit better. So I would simply, since these are both 5th roots, I can write this as the 5th root of 96 divided by 3, which would simplify to the 5th root of 32, and then if we were to the 5th root of 32, that would just be 2. So that one works out pretty nicely. But see how much easier that is if we were to use that property first, and then we can get that, as opposed to doing it individually. That'd be a lot messier because then you're dealing with irrationals. Okay, so now we're going to take some of these and write them in simplest form, and we're going to be using a combination of both real numbers and variables. So this first one to the left, we have the cube root of 104 and then y to the 7th. So when I do this one, I want to look for groups of 3 to pull out. Now the prime factorization of 104, so if I were to write this out here, I'll just do this long ways so you can see what that looks like. Is, oops, little error there. It's simply going to be 2 times 2 times 2 times 13 would give us 104. And then with y to the 7th, that's just going to be y times y times y times y times, that's 1, 2, 3, 4, 5, 6, 7 y's. Okay, and I'm just going to be pulling out groups of 3. So I have a group of 3 2's here, and then I have 1 and then 2 groups of y's there. So when I do this one, when I simplify it, I can pull out a group of 2, okay, and then 2y, so 2 times y times y, and then I'm left with the cube root of 13 times y. So 13 times y. So I multiply everything out in front first, the coefficient first. So that'd be 2y squared, cube root of 13y. Or we could simply say, oh, well, how many times, for the variable, how many times does 3 go in the 7? Oh, it goes in there 2 times with 1 left over. So we don't have to write out the y's all the time like that.
B, what I would do is I'm going to go ahead and break this up into 2 separate cube roots. So I'll have the cube root of 10 m to the 4th over the cube root of 81 n to the 10th. Okay, so I'm going to now simplify these cube roots. Pull out anything I have groups of 3 of. So in the case of the numerator here, I have m to the 4th. Okay, this could be written as m cubed times m. Okay, so therefore I would say I can pull out an m because I have a group of 3 m's times the cube root of 10, and I'm left with an m on the inside. And there's no groups of 3 of anything for the 10, so I leave that alone as well. So in the case of the denominator, the 81 can be written as 3 to the 3 cubed times 3, okay, or 3 to the 4th. I wrote it this way because I do have a group of 3 3's, okay, and then n to the 10th can be written as n cubed times n cubed times n cubed times n. So I have 1, 2, 3 n cubes that I can pull out. So in the denominator, I can pull out a 3 because I have a group of 3 3's. So I have 3, and then I can pull out an n cubed. So that would be 1n, another n cubed, so that's 2 n's, or n squared, and then 3 n's makes it n cubed. So then I'll be left with the cube root of what's left over. In this case, a 3 and an n. So the cube root of 3n. Okay, so at this stage here, I'm going to be, I can't have a radical in the denominator. You know, just like when we were dealing with square roots, we didn't leave a square root in the denominator. I can't leave any sort of radical, no matter what the root is. So the idea behind this is, okay, I have the cube root of n, 3n. So what I want to do is I'm going to ask myself, well, if I need groups of 3 to pull something out or take a cube root of it, how many more 3's am I going to need? Or how many more n's am I going to need? So if I already have 1 3, I'm going to need 2 more 3's. Okay, so 3 squared. And I'm going to need 2 more n's. And what I do on the bottom, I do on the top as well. So 3 squared, or 9, n squared. Thus, that leaves me with the numerator, m cube root, Okay, so 9 times 10 gives me 90. And then mn squared. Then the denominator, I have 3n cubed, and then I have the cube root. Okay, so I have 1 3, I'm putting in 2 more 3's, so I have 3 cubed, and then I have 1n, I'm putting in 2 more, n cubed. Well, basically, the cube root of 3 cubed is 3, and the cube root of n cubed is n. So I'll pull those out and multiply with what's in front here. So, and there's nothing I can do in the numerator to simplify that, so that stays the same. So my final answer in this case is going to be m cube root of 90mn squared over, okay, so I'm pulling out another 3 here, so that's going to give me 9, and then pulling out another n here, so that's going to be n to the 4th. And we no longer have a radical in the denominator. It's ugly, it's an ugly answer, but it would be our simplified answer. So I would just box this guy in. And this just takes a little bit of practice. The more you do, the better you get at it.
Okay, so in example 4, I have 32 m to the 5th, n to the 30th, and I just want to simplify this. So I can do the power of a power property. So I'll have 32 to the 1/5 power, and then 1/5 of, or 5 times 1/5 is just 1, and then I'll have n, and that's going to be 30 over 5. That'll just be 2m and then n to the 6th. Okay, now this next one we're going to go ahead and simplify. I'll start off with the coefficients here. 7 into 56 is going to give me 8. And because this is the denominator is a to the 5/6, and the numerator here, I'll just rewrite this. This is a to the 6/6 because it's 1, and that's 5/6. And then I'll have b to the 3/4, and then c to the -3. Well, that's going to go up here as c cubed. So then I'll evaluate the a's, and I'll subtract it, which will just leave me with a to the 1/6, b to the 3/4, and then c cubed. And that one is simplified. Okay, so the last couple, we're just going to be doing some basic addition and subtraction using rational exponents and root. So we'll start with this, and the key is that you can only add and subtract if the variables and exponents are the same. So this case I can do them. Addition and subtraction are very picky, you have to be very specific as what you can add and subtract. So I would simply add these together, and that would give me 23, and then it's just a to the 4th and then b to the 2/3. Okay, and that's it. Now these I cannot subtract because they're not the same. The radicals are not the same. So but I could at this juncture simplify them. So the first one I have 10, and 4 through to 5 I can't do anything with, but I can pull out a total of I have one group of 4 s's, so I'll have s, and then that leaves me with the 4th root of 5, and then since I pulled out 4 s's, that leaves me with 3, so s cubed minus, and then s. Okay, so looking at the 80, I can simplify the 80 because if I were to if I were to find the prime factorization of 80, so we could say, well, that's going to be 4 times 20, and that's going to be 4 times 5, and that's 2 and 2, and that's 2 and 2. So I have a grouping of four 2's here. So I can actually plot a 2 and I'd be left with a 5. And so I'll write, oh, that's going to be actually minus 2s and then 4th root of 5s cubed. But now when I look at it, I notice that my radicals are indeed the same. So I can indeed subtract these. So I have 10s minus 2s, and that's going to leave me with 8s and then 4th root of 5s cubed. And that is simplified. All right, so anyway, that is applying properties of rational exponents. Till next time, I'll see you on the flip side.